Okay, so number 12 says find the tangent line equation. So we start off, we need order pair, we need slope. To get to the slope, we have to find the derivative. To get to the derivative, what's involved here if we want to find the derivative? Particle, yep. Okay, what's the derivative of e to the negative x?
Negative x.
Yeah, so e to the u times u prime, right? So the original function will show up in your derivative. All right, so g and f are easy. You just copy those down. And then g prime, what's the natural log x of x's derivative? Yeah, u prime over u, right? I don't really care about cleaning this up because I don't really, it's not asking for the derivative function. It's just asking me for tangent line equation. So what's my next step? What do I want from this derivative? Yeah, I want my slope. No, so plug 1 into the derivative. Okay, so negative e to negative 1, that's just 1 over e. Well, what do you know about natural log of 1? 0, right? So that's nice. That's going to wipe that whole thing out. Anything times 0 is just going to be 0. Plus e to the negative 1. And so I can leave it as f prime of 1 is 1 over e. So I have my order pair, I have my slope, point slope form, and that's my answer. Okay, so I just want to make sure I went over that last problem from worksheet 1 before we started worksheet 2. Okay, all right, let's go to worksheet 2. Okay, so how would you start number 1? Expand, okay. So you guys can take your first steps. I just want to kind of circle around the room, make sure that these steps make sense and help you out if you have any questions. I'll go over each problem, but I just want to kind of see you guys start these problems. And we can take care of that radical, right? Rewrite that as parentheses raised to what? 1 thing. Okay. You can use your worksheet 1 to just similar steps. I guess so everything's on there. Yeah, it's good something. Okay, once you have your equation expanded, then your derivative feels a lot easier. Thanks. Okay, any questions with one? Okay, take a look at number 2. Y is equal to the x root of 3 plus 4x squared fifth. Okay, what can we do first? Okay, maybe let's rewrite this problem, right? Okay. So what would this look like in a different form? Okay, good. Okay, so I want us to look at this problem and think about what category does this fall under? How do we approach a problem like this? Good, right. So this is not a power rule problem. This is not chain rule. Okay, this is, yeah, natural log and implicit. This is also not an exponential with a base, constant base raised to exponent variable. This is a variable raised to a variable, right? So we have to understand that. But I'm going to do one more thing here before we take the natural log of both sides. I'm going to rewrite that exponent in a form that will be helpful for our next step. How can I rewrite this 5 over x? What's another way of writing 5 over x? Yeah. And the reason that we may want to do that is because if we leave it as 5 over x, we may feel like, oh, we got to go through quotient rule there, but there's no need for quotient rule for 5 over x, right? Eventually, when that comes down, we can rely on just power rule. But now, okay, next step, natural log of both sides, because we can't handle a variable raised to a variable in this current form. Now that we have a log property, log expression, what can we do with that 5x to the -1? Yeah, move it down. All right, so this is no calculus here. All we're doing right now is creating an easier form for the calculus portion to work.
Are you allowed to keep it in 5?
You could,
Just like expand it out.
I would say if you did not do that, you would have to do it anyway. Otherwise, you'll be forced into quotient rule. I feel like students prefer another rule besides quotient rule. But yeah, you can do it that way.
Like when it's like one, like if it's just like 1/5, how come you can just like multiply it out?
Because it's a coefficient, it's a number, right? But if it's a variable, I got to deal with that variable, right? Either I move it up or I have to leave it down. So, but yeah, it's a good question. If it was x over 5, right? If it was x over 5, then I don't really care because I can just make it 1/5 x. But here, if I leave it as 5 over x in this current form, the only way derivative wise is going through quotient rule, and we prefer not to go through quotient rule, especially if we can avoid it easily with bringing it up and going through power rule. Okay, good. So now we're ready for our calculus portion. Natural log of y becomes what? What's the derivative? 1 over y and dy dx. A little bit of implicit here. Okay, and the right side, there's no way of avoiding this. We have to go through what? Product rule, right? Product rule. I mean, yeah, power rule and then u prime over u, but product rule here. So whenever you have a variable raised to a variable and you go through log differentiation, just know that there's product rule that's going to be waiting for you at the next step. Okay, so see if you can work through those steps there. And just know that with log differentiation, your answer will just be a little messier, but that's okay. As long as you have some version. I think the only thing I'm going to ask you for is when you present your answer, resolve your negative exponents. Okay, that's pretty much the only thing I'm going to ask for. But if you leave your answer unsimplified, I'm not going to take off points because of that. Okay, so f prime is just power rule. And then the g and the f, we don't change. When we get to g prime, we got to go through u prime over u. Okay, so we're done with the calculus after this step. Now we're just trying to solve for dy dx. We want to move that y over. Remember, y is still only a temporary variable, so we got to bring back our original variable x. Do a little bit of cleanup here, maybe merge it into one fraction, and then I'll push the x to -2 back down to the denominator within each fraction. Okay, but the important thing is being able to recognize the need for log differentiation, right? I want us to be able to look at a problem after you rewrite it and be able to recognize, okay, this is a variable raised to a variable. I don't do power rule. I don't do chain rule. I don't do exponential rule. This is a workaround. I got to go through log differentiation. And after that, there's product rule. That's always going to wait. That's always going to be applied as well.
It's like inevitable in these such problems. Like,
Right. It's a product rule is inevitable, especially if you have a variable raised to a variable. Once that variable comes down, you end up with two variables multiplied. So you have to go through product rule. Okay, numbers 3 and 4 are inverse function derivatives. So see if you can work through 3 and 4. Very similar to the worksheet that we did from Monday. I'm just changing the numbers a bit. I may not even have changed numbers for number 4. But yeah, see if you can try it on your own first, right? And then have one more worksheet for us tomorrow. And the hope is for tomorrow, we can treat tomorrow as a mock quiz and just have you guys try the problems without any other worksheets and just see how much you can do. And that, I think that will kind of give us a good feel for how well we're prepared for Friday's quiz, right? So tomorrow, we'll treat tomorrow like a mock quiz. I will still go through each problem, but I want to see how much we can really do on our own without any help. Right, remember, we start at the bottom corner here. Whatever x value that they give you is the x value of the inverse, but it's really the y value of the original function. And then from there, you can start filling in the rest of your chart. So that comes 6. That's the one. So 6 is the x. 6 must be the because this is wrong with place and so like that split that you got that 3. That's the split of the Six is the next value. These will be the same because they're both from 7. So those 4 to 6 is not going to be 7. So 6, 6, and 6. So these will be the same here. Okay.
Six also it's like with that function, it's six is big. Should be like use six. Once we do it, it's not going to. That's so much. Add one six for this. This is gonna make you scratch it. This one's. Guess I'm trying to shut zero. And you need to screw up what that happens. That's still.
Okay, I'll walk through these problems. Sure you guys are okay with these, but walking around, it seems that most of us are doing pretty well. But want to make sure everybody's clear. So we're looking for f prime of 6. That's the goal. So whatever goal I'm looking for, it's going to be in the bottom corner. Now, this is talking about the x value of my f graph, which is in this case my inverse. So it must be the same point since we're talking about the same graph. But g and f are inverses of each other, so the difference is going to come with your g function being a different location of that 6, right? So if 6 is the x value of my function, 6 is the y value of my g function. Right, so this is always the starting point, right? We can do this just by knowing what the target x value of your question is. So now we can look to see, okay, what information is provided for me. Some of this is not going to be useful. 6, 3 doesn't fit this, so I can cross that out. But 3, 6, that's an order pair that I can use. So I know there's an order pair of 3, 6, which means that there must be an f graph of 6, 3. So this is going to help me move forward because I know that if I have the x value of my g graph, I can figure out the slope of my g graph at the same location. So g prime of 3 is -1/4. G prime of 6 is not going to be useful for us. So now I can use that number to help me, right? If the slope of my g graph is -1/4, then the slope of my f graph must be what? -4. Just the reciprocal, the sign stays the same. Yes.
If it says g of 6 equals 3, why don't you just plug in g of 6 equals 3? Like, why don't you just plug?
Because that is not the corresponding point, right? So here's the idea is that there's an order pair on the f graph that is 6, 3. Okay.
How do you know if it's on the f graph? If it says it's on the.
Well, it says find f prime of 6. So our goal is to figure out what is the slope of the f graph at 6. But we're relying on the information on the f graph, g graph, sorry, to figure out what that slope is. So we have to use the inverse relationship to help us get there. So I know that there's an order pair here that is at 36. So if I can find the slope of the g graph at 36, then that slope is going to lead me to the slope of the f graph at 6. So the slope of the g graph at 3 is -1/4. I know this is not accurate here, but the slope is -1/4. So then the slope of this must be 4. Right, so we really have to, we're relying on these corresponding points and their numeric relationship of their slopes to help us get from one to the other. Okay, good. Any other questions with 3? Yeah.
F6 equals 3, where'd you get?
Because if there's an order pair of 3, 6 on the G graph, there must be an order pair of 6, 3 on the F graph. Because they're inverses of each other. So if these are inverses of each other, their order pairs will always be flip-flopped.
It's kind of like what's the role? A little bit.
Yeah, kind of, right? So if there's if these are really inverses of each other, if there's an order pair of 6, 3 on one, there must be an order pair of 3, 6 on the other, right? If they and the way that we know they're inverses of each other is because this first line here, f of g of x equals x. So that tells us that there's that relationship between f and g, and we can establish that this must be true.
But then like, what's the G of 6 equals 3 for? If we only use G of 3 equals 6, how do you know not to use the first one?
Because we're looking for f prime of 6. We're trying to find an order pair that has a relational similarity to f. So some of these order pairs are just distractions, right? They're not part of this chart. There may be an order pair of 6, 3 elsewhere, but that's not part of our problem. Okay, number 4. Okay, same idea here. We know that f and f inverse, there will, if f and f inverse are inverses of each other, their order pairs will be flip-flopped. So here I'm going to find the derivative of f inverse at negative 15, sorry. So I know negative 15 is the x value of my inverse function, which must mean that negative 15 is the what of my f function? The y. So now I can use that negative 15 to help me find what I'm looking for. And so how can I use my function to help me get to my next step? What's my next step? In for the y, right? The negative 15 is not the x value of my function, it's the y value of my function. Because that negative 15, even though it's showing us as the x value here, we know the x value of my inverse must be the y value of my function, right? So and now we just have to go search for that x value. Let me bring everything over to one side and now it's a matter of guess and check. It's not going to be factorable, but we should not have a difficult time finding that x value. It'll be an easy integer value close to 0. So does 0 work? 0 minus 0 plus 16 is that equal to 0? That doesn't work. 1 doesn't work. Negative 1 doesn't work. Okay, what about 2? Negative 2. So negative 2 cubed minus 2 times negative 2 squared plus 16. So that's negative 8 minus 8 plus 16. So that works. So if I know that my order pair is negative 2 at x, then I know that negative 2 must be the y value of my inverse function. So if I can find f prime of negative 2, then that slope will lead me to the slope of the inverse at negative 15. So how can I find f prime of negative 2? Yeah, find the derivative. Okay, so f prime of x There's my derivative. Insert -2 in to get my slope. +8 is 20. So if the slope of my F graph is 20, the slope of my inverse at -15 must be 1/20. All right, number 5. What should we do first with number 5? Expand, okay. There's a hidden base here. This is base 10, okay? So expand like how you did with number 1, very similar. It's just the derivative rule looks a little bit different, right? It's still u prime over u, but with a little coefficient adjustment in front. Okay, so try those steps. So these are the expansion steps before the derivative comes into play. Question property. And now we can do u prime over u, but log base 10, there's a 1 over natural log of 10 that has to be in front. Coefficient times 1 over natural log of 10 times u prime over u. Coefficient of 2 stays 1 over natural log of 10, and then u prime over u. Okay, any questions with the steps? Okay, take a look at number 6. These are the 2 newest rules. But we have to make sure we involve what rule as well for number 6. Product rule, yeah. And the rule that we make sure we remember, we do have an exponential rule to keep in mind here. So a to the u looks a lot like e to the u, but there's a coefficient adjustment that needs to be in front, and then the rest just feels like e to the u. So the original function is going to show up times exponential derivative. A to the u times u prime. All right, try number 6. And again, your derivative will just be messy here. There's not a whole lot of cleanup that we can do. So 3 to the 4x becomes natural log of a times a through u times u prime. The g and f stays the same. G prime though, log base 4. So there's a conversion that's happened. So 1 over natural log of 4, and the rest of it feels like natural log u prime over u. But to get to u prime, I gotta clean this up, right? That's really x to the 1/3. Gotta go through power rule. 1/3 x to the negative 2/3. Just resolving my negative exponent here, pushing that x down to this denominator space. Oh, yes, you're right. I didn't catch that. That should be a negative. Yeah. Yes.
After like 4 times natural log of 3, why would you do 3 to the 4x instead of just 4? Like, how did you, I just wanna know.
Yeah, sorry, question again?
Like for, in the beginning of the problem, how did you get the 3 to the 4x in the first? Like, why wouldn't it just be 4?
Right here.
But isn't that from the second side?
Well, let's see. It's f prime g plus f g prime.
Okay.
So my f function is just copying down my f expression, right? Is that your question? Like why that 3 to the 4x is there?
I just thought it would be like after an addition sign, because it, like, I don't know why it's multiplied in the beginning.
Why this is being multiplied?
Like in the beginning, like of the actual answer.
Oh, right here,
Like down,
this part.
yeah, that.
Oh, okay.
How did it get there?
Oh, this part, I just rearranged it. I don't have to. I just like my coefficient in front if possible. But I didn't do anything from here to here. I'm just rearranging. Okay, good. Any other questions with 6?
From that actually trying to create
Oh, from here to here. So I'm putting all the numerators together. and all the denominators together. So I'm gonna circle my numerator. This is my only numerator here. All these are denominators. So this is in the denominator, this is in the denominator, this is in the denominator, that's in the denominator, so I should put it all. I can do that because these are all being multiplied. There's no plus or minus within each of these terms, so they can all be nicely stacked. But as soon as I introduce another, this 5 minus cube root of x, this doesn't affect anything, because that's just, I consider that as one thing, so. Okay, number 7 says use log differentiation to find the derivative. Now, this problem does not need log differentiation, right? It's just an option. Because we could go through chain, product, quotient rule. It's not like number 2 where there was no other option. We had to go through log differentiation because it's variable, rate, and variable. Log differentiation can also be used for problems where we can avoid rules. So if you see this on the quiz, this could be one where I would tell you to use log differentiation because I know that there's another method that you can do. But with the variable raised to variable, that's the only way that you can approach that problem. But here, we'll take the natural log of both sides. We'll take advantage of all of the expansion properties that is available to us. And then and then once we expand everything out, then u prime over u the rest of the way. So this is really the same thing as natural log of a times b over c. So I can make this natural log of a plus natural log of b minus natural log of c. And then once everything is nice and expanded, we can also bring the exponents down. And then we just step through u prime over u for each of the derivatives. Okay, so much like number 2, this one, there's no product rule that we have to go through, not like number 2. So this one, just 1 over y dy dx, and then u prime over u for the rest of it. You'll bring that y over to the right. Your derivative will look really messy, but you'll leave it in that form. Okay, any questions with number 7? Okay, number 8. There's 3 things that I want you to point out. What is involved here if we want to find the derivative? dy dx. Yeah, so implicit. Okay, now go through implicit. How many y's how many dy dx do we expect to show up? 2. Okay, what else? Product rule, not that one. Well, the product rule derivative is for the 4xy. Oh, okay. But what would you do with the natural log of x squared y? Expand, right? So this one I would do first to take care of the before the calculus sets in. Once you get that natural log of x squared y expanded, there's no way around product rule for the 4xy, so we got to go through 4xy. Sometimes I see students apply log differentiation for problems that are not meant to be log differentiation. So there's only two types for log differentiation. One is where I tell you explicitly to use it, okay? And the other is a variable raised to a variable, right? Those are the only two cases that you will introduce logs into the problem. Otherwise, you just have to take whatever problem gives you and just start with that. Okay, so either I tell you to use it very explicitly, or a variable raised to a variable. Otherwise, we should not have to involve natural log into introduce something new to the problem. We just have to solve the one in front of us. Okay, so that's our expanded form. Then we do f prime g plus f g prime. And then we do u prime over u for both of these. What happens to the 7?
0.
All right, so we'll finish this up tomorrow. I have another worksheet for us and then quiz on Friday. So hopefully we're getting to that point where we're beginning to feel comfortable with each of the types of problems that we're seeing. We'll also review our derivative rules tomorrow as well. Okay, go get your comments. What about